I apologize about that. Says we have a 30 centimeter by 60 centimeter rectangular circuit consisting of a 15 ohm resistor is perpendicular to a uniform magnetic field that starts out at 2.65 Tesla and steadily decreases at 0.25 Teslas per second. See the figure. While the field is changing, what does the ammeter read? So what they want us to figure out is the current. So let me draw the picture. They have the magnetic field going into the page. And they said initially the magnetic field was 2.65 Tesla. Okay. And then we have, now this is important, it's a 30 by 60 rectangular circuit loop. So it's a loop. How many turns are in a loop? Yep. One. You're going to need your imagination on this 30 by 60 because my diagram is horribly not to scale. So 30 by 60. The resistance was 15 ohms, and then there's an ammeter here. Okay, so the magnetic field starts off at 2.65 Tesla, and then it says that it's going to steadily decrease at 0.25 Teslas per second. So what they give us is that this change in the magnetic field strength over the change in time is 0.25 Teslas per second. And since it is decreasing, then it is negative. Okay. So if the magnetic field is decreasing, then what's happening to our magnetic flux? Yep. And so then to oppose the change, then which way does our B induced go? And therefore, which way does the induced current go in our loop? So with our flux decreasing, then to oppose the change, then the B induced gonna want to go with the B that is going down, make it go back up to oppose the change. And so since our B, again, all we care about is inside the loop, B goes into the page. So if we're going to go with, then the B induced also goes into the page. Right hand rule. Fingers are the B, thumb is the I. That's the way I like to do it. So the induced current goes clockwise. Decreasing, this definitely goes down. We need to go with. B is in, B reduced is in. Okay. Definitely gonna need a little more practice on this one. All right, so we got that our induced current is gonna go clockwise. And so when we go to calculate this, then our Faraday's law, the average induced EMF is minus N times this, change in the magnetic flux over the change in time. Okay. And so the way that this one goes is that we would go in and plug in for our flux. So this is going to be -1 because there's only, it's a loop or a circuit is I think the way they said it. It's a loop. So it's only one. And then what we're going to consider is the change in our B times A times the cosine of our angle. Okay. And so we're going to pick an area vector. Which way do you want our area vector to go? Is it going to go into the page or out of the page? What do y'all think? Okay, into. And if since the A goes in and the purple B goes in, then our angle here is 0 degrees. Cosine of 0 is just +1, like so. Okay. Now, what we would talk about is that when we consider the change in this flux, then the B changes, but the A does not. It's a 30 by 60 centimeter rectangular loop. So A does not change. The +1 also does not change. And so we can pull this out of the change in quantity. So it will still remain negative. I'll pull the A out and then the +1 comes out and I'm left with the change in B over the change in time. And that's what they told us was the rate at which the magnetic field decreased with time. Okay. And they said that that was constant. And so this is why the average is the value. And then we can put this stuff in like so. And so this will be minus from the Faraday's law. The area is 30 times 60. So we'll take 0.300 times 0.600. Got to make it SI to make sure it all works out. And then this, change in the magnetic field per time is the negative 0.25 Teslas per second. Now, what'll happen is this minus sign from Faraday's law and the negative from the decreasing on the change in the B over the change in T, they cancel. And this gives me 0.3 times 0.6 times 0.25. Okay, so 3 and 6 are what, 18? So that's 0.18. This is a quarter of that. There we go, 0.045. 0.045 volts. And it's now positive. Positive tells us the direction if we use this rule. Okay. And then to get the current, which is what they asked for, then we use the Ohm's law. So we'll do that. The induced current is our induced voltage over the resistance. So this is the plus 0.045 volts over 15 ohms. 15 goes into 45, what, 3 times? Plus 0.003 amps. I need zeros after that, otherwise I don't have enough digits, but it'll be all right. You get the idea. So 3 milliamps is our answer. And since it's all constant and uniform, then the averages are the values, and I can drop the averages. And the plus sign tells me the direction. So since I picked the area vector to go into the page, and I put my thumb in that direction, then my fingers wrap around in the positive circulation, which is going to be clockwise. So that means this way is positive. And our answer came out what? Positive. So then the current should go clockwise. So this is the thing, is that the doing the delta B over delta T and pulling that out, a change in magnetic flux over time. I think you need to see that to be able to do that. I think once you know that you can, oh, A is constant, out it goes, or if B was constant, out it would come, and you'd leave the A in or something like that, however they want to do it. So